All right, so welcome back for what I'm hoping is the final part of section 3.3. This is part 5. And in part 5, we're going to take a look at the idea of higher order derivatives. All right, so far we've taken the derivative function, but could we take another derivative and another and another and another? Mathematically, since the derivative of a function is a function, you could take another derivative. And since the derivative of a derivative is, again, a function, you could take another derivative. So mathematically, yes, of course you can do it. The question is, why would you care? What information would this give you? And why would you do it? I mean, the first derivative gives us information about the original function. It tells us the rate of change for that function for any point on that, in that function's domain, on that function. What would the second derivative, that's what we call it, the first derivative, the second derivative, right? What information would that give us about it? And as we move through this course, what we're going to find is there are going to be applications where higher derivatives give us information, and it makes sense. Now, one of the first ones we're going to run into is the relationship that exists between position functions, velocity functions, and what's called acceleration. Okay? By definition, acceleration is a measure of the change, the rate of change of velocity. If you are accelerating, that means that your velocity is increasing. And if you are decelerating, that means that your velocity is decreasing. So the idea of talking about acceleration or deceleration, right, a positive acceleration or a negative acceleration, is the rate of change of velocity. But anytime something is the rate of change of something else, calculus-wise, what you're talking about there is you're talking about taking a derivative. So to say that acceleration is the rate of change of velocity is to say that acceleration is the derivative of velocity. But velocity is the derivative of position. So that means that acceleration, the acceleration function, is the second derivative of the position function. So here's how it goes. You start with position. And then the derivative of position, the first derivative of position, is velocity. And then the second derivative of position, which is the derivative of velocity, is acceleration. Now, I bet there's at least one person out there wondering what happens if you continue. What would happen if you took a third derivative of this? An S triple prime, or a V double prime, a second derivative of velocity, or an A prime, A being acceleration. You would get the jerk. Okay? Now think about this. It's called the jerk because it is the rate of change of acceleration. So suppose you're on the on-ramp, getting on the freeway, and you have your foot on the gas, which means that you have positive acceleration. Your velocity is increasing. And you look to your left and you see a large truck. You have two options. One, you can hit the brake and make a rapid change in acceleration to slow you down, decelerate, or you can hit the gas harder and make a rapid change in acceleration positively to make you go faster to either get in front of or get behind that truck. But either way, whichever decision you make, hitting the brake or hitting the gas, is going to cause a rapid change in acceleration, and you're going to feel that jerk. Either a jerk pushing you back in the seat if you rapidly accelerate, rapidly change your acceleration, or a jerk as you're pushed forward against your seatbelt when you rapidly decelerate or change that acceleration in a negative sense. Okay? Well, now you're asking what happens next. The next derivative is snap, the one after that is crackle, and the one after that is pop. I don't make these things up. Okay? You can Google it if you don't believe me. Position, velocity, acceleration, jerk, snap, crackle, pop. Okay? All right, so let's talk about derivatives. When we take higher order derivatives, the notation changes. Okay? Our first derivative is just y prime or f prime or dy dx or this business, which we don't see too much here, but we do see occasionally. Our second derivative is double prime. 1 apostrophe for first derivative, 2 apostrophes for second derivative, 2 apostrophes. If you're going to use the Leibniz notation, we use this exponent notation. The 2 in the numerator says that we are taking the derivative twice. It's applied to the d. That means we differentiate it twice. The 2 in the denominator is applied to the x, meaning that when we took the derivative, we took it with respect to the variable x both times. That same notation is mirrored here as well as here, for a d to mean twice with respect to x. A third derivative, well, 1 apostrophe, 2 apostrophes, 3 apostrophes, 3 apostrophes, or instead of a 2, a 3 in the exponent position here as well. Right? Beyond 3, we don't use apostrophes anymore. So if you needed to take a fourth derivative for some unknown reason to me, you would use this notation. Exponent parentheses around the number. Okay? The reason being is once you get beyond 3 apostrophes, it gets kind of ugly. 1, 2, 3, 4 apostrophes, it just gets too many. So the people who make these decisions, I don't know who that is, they decide to use this different notation. Again, that mirror that notation here, as well as here and here. In fact, you could take any derivative. So if someone wanted to, they could do this and take the 57th derivative of some function. Now, I have no idea why anyone would need to do that. Maybe there's an application out there. I can't think of one offhand where you would need to take that many derivatives, but it is possible to take that many derivatives. Right? And if you can take that many derivatives, then the notation is just to put that n, that number derivative, into the parentheses or appropriately place it over here in those Leibniz and operator notation. All right, so let's take a look at an example. Okay. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott just demonstrated that with a feather and a hammer falling at the same rate on the moon. The position function for each of these falling objects is s of t equals negative 0.81 t squared plus 2, where s of t is the height in meters and t is measuring time in seconds. What is the ratio of Earth's gravitational force to the moon's gravitational force? All right, so if we're going to make a ratio of the gravitational force, we need to find the acceleration force of gravity on the moon and compare that to Earth. So I know that the position function for Earth, okay, if we're talking meters and seconds, is s of t equals negative 4.9 t squared. Okay. Actually, you know what? I'm even going to do you one better. Negative 1/2 g t squared plus v sub 0 t plus s sub 0, which means that s prime of t, which would be our v of t, is going to be negative gt plus v sub 0, and then s double prime of t, which is going to be v prime of t, which is going to be a of t, which is be negative g. Now, when we are working in meters, g was 9.8, so negative 9.8 meters per second squared, meters per second per second. Okay? We have the same information for the moon. A position function, that is s of t equals negative 0.81 t squared plus 2. Okay? The fact that there's no t term in the moon one tells me that this thing was just dropped. It had no initial velocity. And this 2 over here on the end just tells me that this thing was dropped from a height of 2 meters, about 6 feet or so. Okay? Now we'll start taking derivatives. S prime of t, which is velocity, v of t, is going to be 2 times negative 0.81. Negative 0.81 times 2 is 1.62, or negative 1.62 t, and the derivative of 2 is 0. Right? That's velocity, but we need acceleration, so we need s double prime, the second derivative, which is v prime, the first derivative, which is a of t, which is negative 1.62. So now that I have the acceleration and the acceleration for gravity on the Earth and the Moon, now I can make a ratio of the Earth to the Moon. Now when it says to make a ratio of Earth to Moon, that means make a fraction with Earth over Moon. So in this case, that's going to be negative 9.8 meters per second squared divided by negative 1.6. Let's try that again. Negative 1.62 meters per second squared. Now clearly the units are going to cancel. I'm going to need a calculator for that, so I'm going to grab my calculator, and let's see. Negative 9.8 divided by negative 1.62, I get about 6. And so what does that mean? Well, it means that the acceleration due to gravity on the Earth is about 6 times as great as the acceleration due to gravity on the Moon, because the ratio of the two is about 6. It's 6.04 and change, so we'll call it 6. So on Earth, gravity is about 6 times as strong as it is on the Moon. Now, if we had talked about the ratio of the Moon to the Earth, that would be Moon upstairs, Earth downstairs, so that would be 1/6, or we would feel 1/6 as much, which would explain why if you look at the videos of the guys walking around on the Moon from back in the day, they look like they're jumping and moving around. It's because the gravity up there is so much less that they can't walk normally. They end up just jumping around, bouncing. This finally brings us to the end of section 3.3. So I'm going to stop this video, and the next time you'll see me will be section 3.4. Have a good one.